Welcome everyone to this presentation on the role of statistics in data science engineering. In today's data-driven world, statistics plays a critical role in transforming raw data into meaningful insights. Throughout this session, we will explore how statistical concepts form the foundation of data science and business analytics. This presentation is designed especially for beginners to intermediate learners. So we will move step by step from basic concepts to real world applications so that you can clearly understand how statistics supports decision making and machine learning. Now let's move our introduction to statistics in data science. Statistics is often called the backbone of data science because it provides the mathematical foundation needed to analyze and interpret complex datasets. Without statistics, data is just a collection of numbers with no meaning. It enables data scientists to make evidence based on decisions by quantifying uncertainty and measuring the significance of results. More importantly, statistics helps transform raw and unstructured data into actionable insights that business can use. It is deeply integrated into machine learning and artificial intelligence, powering everything from data cleaning to model building and evaluation. In simple terms, statistics is the language that helps us understand what data is trying to tell us. Now let's come towards the types of statistics. There are two main types of statistics, descriptive and inferential. Descriptive statistics focuses on summarizing and describing data. It uses measures like mean, median, and mode, along with charts and tables, to answer the question, what happened? For example, calculating the average sales of a company over a year. On the other hand, inferential statistics goes a step further by making predictions about a larger population based on a sample. It uses probability, hypothesis testing, and confidence intervals to answer what could happen. For instance, predicting election results by surveying a small group of people. Together, these two types help us both understand past data and forecast future outcomes. Now let's come towards the key statistical concepts. Let's now understand some key statistical concepts. The mean represents the average value and is calculated by dividing the sum of all values by the total count, but it can be affected by extreme values or outliers. Variance measures how spread out the data points are from the mean, while standard deviation, which is the square root of variance, gives a more interpretable measure of spread. Skewness tells us whether the data is symmetric or tilted toward one side, either left or right. Outliers are extreme values that differ significantly from the rest of the data and can distort analysis if not handled properly. These concepts are fundamental because they help us understand the shape, spread, and reliability of data. Now let's come towards the probability fundamentals. Probability helps us measure uncertainty by assigning a value between 0 and 1 to events, where 0 means impossible and 1 means certain. Most real world events fall somewhere in between. Conditional probability, written as P A by B, represents the likelihood of event A occurring given that event B has already happened. One of the most important concepts here is bias theorem, which allows us to update our belief when new evidence is available. This formula is widely used in applications like spam detection, medical diagnosis, and recommendation systems. In data science, Probability provides the foundation for making predictions and handling randomness effectively. Now, let's move towards the data distribution and normal distribution. Data distribution describes how values are spread across a dataset. The most important distribution is the normal distribution, which is a bell-shaped and symmetric curve. It follows the 68-95-99.7 rule, meaning that about 68% of data lies within one standard deviation from the mean, 95% within 2, and 99.7% within 3. Another type is uniform distribution, where all outcomes are equally likely, like rolling a fair die. Skewed distribution occur when data is not symmetric and has a longer tail on one side. Understanding distributions is crucial because many statistical tests and machine learning models assume normality, and choosing the right model depends on the data distribution. Hypothesis testing. Hypothesis testing is a structured method used to make decisions based on data. It starts with two hypotheses: the null hypothesis, which assumes no effect or difference, and the alternate hypothesis, which suggests that there is an effect. After collecting data, we calculate the p-value, which tells us the probability of observing the results if the null hypothesis were true. We then compare this p-value to a significance level, usually 0.05. If the p-value is less than this threshold, we will reject the null hypothesis. For example, if we are testing a new drug and get a p-value of 0.02, it indicates strong evidence that the drug is effective. Now let's move towards the correlation versus causation. One of the most common mistakes in data analysis is confusing correlation with causation. Correlation means that two variables move together, either positively or negatively. For example, as study hours increases, grades may also increase, showing positive correlation. Under negative correlation means one variable increases while the other decreases, such as exercise and weight. However, correlation does not imply causation. A famous example is that ice cream sales and drowning rates both increase in summer, but ice cream does not cause drowning. The hidden factor here is temperature. Therefore, it is important to identify underlying variables before concluding cause and effect relationships. Now let's move towards the regression analysis. A regression analysis is used to understand relationships between variables and make predictions. The most common type is linear regression, which fits a straight line represented by the equation y equal to mx plus b, where m is the slope and b is the intercept. It is widely used in forecasting, such as predicting sales or demand. The R squared value indicates how well the model fits the data, with values closer to 1 showing a better fit. Multiple regression extends this concept by using multiple independent variables. For example, predicting sales based on advertising, price, and season simultaneously. Now let's come towards the sampling techniques. Sampling involves selecting a subset of a population for analysis. Random sampling gives every individual an equal chance of being selected, making it the most unbiased method. Stratified sampling divides the population into groups and samples from each group to ensure proper representation. Systematic sampling selects every nth individual, which is simple but may introduce patterns. Cluster sampling divides population into clusters and selects entire groups randomly, which is useful for large and geographically spread populations. Good sampling techniques are essential because they save time and cost while ensuring reliable results. Now let's move towards the statistical tools and libraries. There are several tools used for statistical analysis. Python is the most popular, with libraries like pandas for data manipulation, numpy for numerical operations, scipy for scientific computing, and scikit-learn for machine learning. R is another powerful language known for statistical analysis and visualization, especially with packages like ggplot2. SQL is essential for querying and analyzing data stored in databases, while Excel is widely used for quick analysis with pivot tables and built-in tools. The choice of tool depends on the complexity of the task and the scale of data. Now we move next towards the real-world applications. Statistics plays a vital role across industries. In finance, it is used for risk analysis, fraud detection, and portfolio optimization. In healthcare, it supports clinical trials, disease prediction, and drug testing. Marketing teams use statistical method for customer segmentation, A/B testing, and campaign optimization. In e-commerce, companies like Amazon use recommendation systems powered by statistics contributing significantly to revenue. This example shows that statistics is not just theoretical, it is actively driving real world decisions and innovations. Now let's move towards the challenges and limitations. Despite its power, statistics has several challenges. Dirty data, including missing values and errors, can lead to incorrect conclusions, and data cleaning often takes most of a data scientist's time. Sampling bias occurs when the sample does not represent the population properly. Misinterpretations such as confusing correlation with causation can lead to false insights. Overfitting is another issue where models perform well on training data but fail on new data because they are too complex. Understanding these limitations is important for applying statistics correctly. Now let's move towards the conclusions and key takeaways. To conclude, statistics is an essential part of data science. It supports every stages of data pipeline, from understanding data to building and validating models. It improves model accuracy by helping in feature selection, assumptions testing, and performance evaluation. Most importantly, statistics enables data-driven decision making by converting raw data into meaningful insights. As W. Edwards Deming said, without data, you are just another person with an opinion. This highlights the importance of statistical thinking in modern decision making. Thank you for attending this presentation. We have covered the journey from basic statistical concepts to advanced applications in real-world industries. Remember, statistics is not just about numbers, it is about understanding the story behind the data. I encourage you to practice this concept using real data sets to strengthen your understanding. Now, I would be happy to answer any questions you may have. Thank you.